You wake up, you breathe, atoms hold. Every single second, trillions of atoms in your body refuse to collapse into nothing. The chair beneath you does not implode. The ground stays solid. But according to classical physics, none of this should work. Electrons orbiting atomic nuclei should radiate energy and spiral inward in less than 1/1000th of a second. Matter should not exist. Yet here we are. What invisible rules stop reality from crushing itself into oblivion? Which quantum barriers keep existence stable? Why does the universe not simply vanish? Niels Bohr's Institute, buzzing with physicists, rewriting reality. Pauli introduced what became the exclusion principle. No two electrons can share identical quantum states. All four quantum numbers must differ. Principal number, azimuthal number, magnetic number, spin number. If two electrons occupy the same orbital, their spins must oppose. One positive 1/2, one negative 1/2. This single rule explains why atoms have size, why matter occupies volume, why you cannot shove two objects into the same space. Paul Ehrenfest saw it first in 1931. He pointed out electrons cannot all crowd into the ground state. They must fill successively larger shells. Freeman Dyson and Andrew Leonard proved it rigorously in 1967. They balanced attractive forces between electrons and nuclei against repulsive forces between electrons and between nuclei. Without Pauli's principle, ordinary matter would collapse. Elliott Lieb and Walter Thirring simplified the proof in 1975 using the Thomas Fermi model. The math locked in. Matter stays stable because fermions refuse to share. This script is researched and factual using sources from the 1925 original publication by Pauli in Zeitschrift für Physik, the 1967 proof by Dyson and Leonard published in the Journal of Mathematical Physics, and the January 2025 retrospective in Chemistry World marking 100 years of the exclusion principle. Now back to the information. Spin 1/2 specifically. The wave function describing two identical fermions must be antisymmetric. Swap two fermions and the wave function flips sign. Positive becomes negative. This is not a choice. This is structure baked into quantum field theory. Bosons behave oppositely. Integer spin, symmetric wave functions. Photons in a laser all occupy the same state. Atoms in a Bose-Einstein condensate merge into one quantum blob. But fermions cannot. Place two electrons in the same quantum state and the math equation spits out 0. The probability vanishes. The configuration is forbidden. As you climb this periodic table, electrons stack into shells determined by quantum numbers. The s orbital holds 2, the p orbitals hold 6, the d orbitals hold 10. Chemistry emerges from electron arrangement. Reactivity depends on outermost electrons. Sodium has one lonely electron in its outer shell. Chlorine needs one electron to complete its outer shell. They bond. Salt forms. All because Pauli's rule forces electrons into specific configurations. As of January 2015, results published in Arciv show the violation probability capped at 5 × 10 to the -6th power per electron, effectively 0. Pauli's principle holds across every test. For Physik, the uncertainty principle. You cannot know both position and momentum simultaneously with arbitrary precision. The product of uncertainties has a floor. Delta x times delta p must equal or exceed h bar over 2. Planck's constant divided by 4 pi. Approximately 1.05 × 10 to the -34 joule seconds. This is wave-particle duality enforcing fundamental limits. An electron is not a particle sitting at a point. An electron is a wave packet spread across space. Measure its position precisely and the wave collapses to a narrow region. But momentum is the Fourier conjugate of position. A narrow position wave requires a broad momentum wave. The electron's momentum becomes uncertain. Conversely, measure momentum precisely and the position spreads out. You cannot pin down both. But orbiting charges radiate energy. Maxwell's equations demand it. An electron circling a proton should emit electromagnetic waves continuously. The orbit should decay. The electron should spiral inward and crash into the proton in about 10 to the -11 seconds, 100 trillionths of a second. Atoms should not last. Delta x decreases. The uncertainty principle forces delta p to increase. Momentum uncertainty grows. Higher momentum means higher kinetic energy. The electron moves faster. This increased kinetic energy counters the electromagnetic attraction. The electron cannot simply fall in. There exists a lowest energy state, a ground state, where kinetic energy balances potential energy. The electron sits in this ground state indefinitely. The atom remains stable. For an electron, mass equals 9.11 × 10 to the -31 kilograms. Kinetic energy comes out to about 13.6 electron volts. This matches the ionization energy of hydrogen, the ground state energy measured in experiments. The uncertainty principle predicts atomic stability quantitatively. The lowest possible energy is not 0. A harmonic oscillator at absolute 0 still vibrates with energy 1/2 h bar omega. Omega is the angular frequency. This zero-point energy is unavoidable. It follows directly from the uncertainty principle. If a particle sat perfectly still at the bottom of a potential well, you would know both its position and its momentum exactly. Position equals the bottom of the well. Momentum equals zero. But the uncertainty principle forbids this. The particle must have some spread in position and some spread in momentum. It must retain kinetic energy. Some over all oscillators, and you get the vacuum energy. The calculation diverges to infinity if you are not careful. Physicists use renormalization tricks to extract finite answers. The cosmological constant problem arises here. Particle physics predicts a vacuum energy density 10 to the 123 times larger than the observed cosmological constant. This mismatch remains one of physics' deepest mysteries. The Casimir effect proves vacuum energy is real. 1948. Dutch physicist Hendrik Casimir predicts that two uncharged parallel metal plates in a vacuum should attract each other. The plates restrict which vacuum fluctuations can exist between them. Only wavelengths that fit between the plates survive. Outside the plates, all wavelengths fluctuate. This creates a pressure imbalance. The vacuum pushes the plates together. In 1997, Steve Lemereau at the University of Washington measured the Casimir force between a spherical lens and a flat plate. The measured force matched quantum electrodynamics predictions within 5%. The vacuum has measurable energy. You need a higher state and a lower state. Energy flows from high to low. Since there is no state lower than the vacuum, you cannot tap it. Free energy devices claiming to harvest zero-point energy violate thermodynamics. They do not work, but you can manipulate vacuum energy locally. Conductors and dielectrics change the vacuum structure. You can measure those changes, just not exploit them for perpetual motion. Protons and neutrons pack together. Protons carry positive charge. Like charges repel, the electromagnetic force should blow the nucleus apart. Inside a nucleus, protons sit femtometers apart. 1 femtometer equals 10 to the negative 15 meters. At this distance, electrostatic repulsion is enormous. Coulomb's law says the force between two protons separated by 1 femtometer is about 230 newtons. That is the weight of a 23 kilogram mass, concentrated on particles 10 to the negative 15 meters apart. It is roughly 100 times stronger than electromagnetic repulsion at nuclear scales. Beyond a few femtometers, the strong force drops to zero. It has ultra-short range. Inside that range, it glues nucleons together. The shell model of the nucleus explains this. Just as electrons fill atomic shells, nucleons fill nuclear shells. Filled shells are stable. Helium-4 has 2 protons and 2 neutrons, both shells filled. Extremely stable. Oxygen-16 has 8 protons and 8 neutrons, doubly magic. Lead-208 has 82 protons and 126 neutrons, doubly magic, the most stable heavy nucleus. Alpha decay, beta decay, gamma decay. Alpha decay ejects a helium-4 nucleus, 2 protons, 2 neutrons. But classical physics forbids it. The alpha particle sits in a potential well. The strong force holds it in. Outside the nucleus, the electromagnetic force creates a Coulomb barrier. The barrier height is about 20 to 25 million electron volts for heavy nuclei. The alpha particle has kinetic energy around 4 to 9 million electron volts, not enough to climb the barrier. The wave function does not drop to zero at the barrier. It decays exponentially inside the barrier. On the far side, a small tail exists. The square of the wave function gives probability. The alpha particle has a non-zero probability to appear outside the nucleus. It tunnels through. The alpha particle collides with the barrier about 10 to the 21 times per second. Each collision has a tiny tunneling probability. Multiply attempts per second by probability per attempt, and you get the decay rate. Half-lives range from microseconds to billions of years. Bismuth-209 has a half-life of 2 times 10 to the 19th years, older than the universe. Polonium-214 has a half-life of 164 microseconds. The Geiger-Nuttall law relates half-life to alpha energy. Higher energy alpha particles tunnel through narrower barriers. They decay faster. Nuclear fusion in stars depends on it. Protons in the sun's core have kinetic energy around 1,000 electron volts. The Coulomb barrier between 2 protons is about 500,000 electron volts. Classical physics says fusion cannot happen. Quantum tunneling makes it possible. Protons tunnel through the barrier, they fuse into deuterium. The sun shines because of quantum mechanics. A sharp metal tip hovers nanometers above a conducting surface. Apply voltage. Electrons tunnel from the tip to the surface or vice versa. The tunneling current depends exponentially on distance. Move the tip closer and current increases. Pull back and current drops. Scan the tip across the surface while measuring current. Map individual atoms. Gerd Binnig and Heinrich Rohrer invented the scanning tunneling microscope in 1981. They won the Nobel Prize in 1986. The device revolutionized nanotechnology. But electron degeneracy pressure holds it up. The star stabilizes. But relativity caps electron speed at light speed. Eventually, degeneracy pressure cannot keep up with gravity. The limit occurs at 1.44 solar masses, the Chandrasekhar limit. Gravity overcomes electron degeneracy. The core becomes a neutron star. Neutrons are also fermions. Neutron degeneracy pressure takes over. A neutron star has a mass around 1.4 solar masses packed into a radius of about 10 kilometers. Density equals nuclear density, approximately 10 to the 17 kilograms per cubic meter. A sugar cube of neutron star material weighs 100 million tons. Arthur Eddington disbelieved Chandrasekhar's result. At a Royal Astronomical Society meeting in 1935, Eddington publicly ridiculed the young physicist. Eddington argued that there must be some mechanism to prevent collapse. Chandrasekhar stood firm. Observations eventually confirmed him. White dwarfs above the Chandrasekhar limit do not exist as stable objects. They explode or collapse. In 1983, Chandrasekhar shared the Nobel Prize in Physics for his work on stellar structure. But quantum mechanics and general relativity clash at singularities. A theory of quantum gravity is needed. String theory, loop quantum gravity, and other candidates compete. None are confirmed. Developed in the 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, they shared the Nobel Prize in 1965. QED is the most precisely tested theory in physics. The electron's anomalous magnetic moment is predicted to 12 decimal places. Experiments match. The s orbitals are spherical. The p orbitals are dumbbell-shaped. The d orbitals are more complex. Electrons do not have definite positions. They have probability distributions. The wave function squared gives the probability density, where you are likely to find the electron. All bonding follows quantum rules. Molecular orbital theory extends atomic orbitals to molecules. The molecular orbitals spread across multiple nuclei. Bonding orbitals lower energy. Antibonding orbitals raise energy. Electrons fill bonding orbitals first. Molecules are stable when bonding orbitals outweigh antibonding. Groups correspond to similar outer electron configurations. Noble gases have filled outer shells, unreactive. Alkali metals have one outer electron, highly reactive. Halogens need one electron, highly reactive. Dmitry Mendeleev organized the periodic table in 1869. He arranged elements by atomic weight and chemical properties. He left gaps for undiscovered elements, predicted properties of those elements. Scandium, gallium, germanium were later discovered with properties matching his predictions. Both rules follow from minimizing energy while respecting the exclusion principle. These exceptions arise from subtle energy differences between orbitals. The 3d and 4s orbitals are close in energy. Small perturbations change the order. The conduction band is empty at zero temperature. The energy gap between bands determines conductivity. Modest conductivity. Doping semiconductors adds impurities. N-type doping adds extra electrons. P-type doping adds holes where electrons are missing. Junctions between N-type and P-type materials form diodes, transistors, solar cells. Free electrons absorb photons across a wide range of frequencies. Metals conduct heat well. Free electrons carry kinetic energy. Specific heat capacity of metals at low temperatures follows the Sommerfeld model. Only electrons near the Fermi energy contribute. Most electrons are degenerate and cannot absorb energy. This explains why metals have lower heat capacity than classical predictions. Ferromagnetism in iron, cobalt, nickel arises from aligned electron spins. Normally, exchange interactions favor parallel spins, but the exclusion principle limits how many electrons can have parallel spins in the same spatial orbital. Ferromagnetic materials balance these competing factors. Temperature disrupts alignment. Above the Curie temperature, thermal motion randomizes spins. Ferromagnetism vanishes. Iron's Curie temperature is 1043 Kelvin. Discovered by Pyotr Kapitsa in 1937. Electrical resistance drops to zero. Superconductivity was discovered in mercury by Heike Kamerlingh-Onnes in 1911. The BCS theory explaining it came in 1957 from John Bardeen, Leon Cooper, and Robert Schrieffer. They won the Nobel Prize in 1972. Certain ceramic materials superconduct above liquid nitrogen temperatures. 77 Kelvin. The mechanism is not fully understood. BCS theory does not explain them. Research continues. Applications include MRI machines, particle accelerators, quantum computers. Alpha and beta are complex numbers. The qubit exists in both states simultaneously until measured. Measurement collapses the superposition. Entanglement links qubits. Measuring one instantly affects the other, even across arbitrary distances. Einstein called it spooky action at a distance. John Bell proved in 1964 that entanglement is real. Experiments by Alain Aspect in 1982 confirmed it. Quantum computers can solve certain problems exponentially faster than classical computers. factoring large numbers, simulating quantum systems, searching databases. Building large-scale quantum computers remains challenging. Companies like IBM, Google, and Rigetti are making progress. Google claimed quantum supremacy in 2019 with a 53-qubit chip. The claim is debated. Practical quantum computers are years or decades away. Atoms would have no size. Without uncertainty, electrons would fall into nuclei. Atoms would not exist. Both principles are essential. They are not arbitrary rules. They follow from the structure of quantum mechanics, from the wave nature of matter, from the requirement that wave functions be either symmetric or antisymmetric under particle exchange. The table you write on, the floor you stand on, the air you breathe, all held together by forces and principles discovered in the 20th century. Classical physics predicted collapse. Quantum mechanics explains survival. Cells operate using chemical reactions governed by quantum mechanics. Photosynthesis converts light into chemical energy. Quantum coherence may play a role. Birds navigate using quantum effects in their eyes. Enzyme catalysis exploits quantum tunneling. Biology is built on quantum foundations. Matter formed when quarks combined into protons and neutrons. Electrons combined with nuclei to form neutral atoms. This recombination happened about 380,000 years after the Big Bang. The cosmic microwave background is light from that era. It shows tiny temperature fluctuations. These fluctuations grew into galaxies. The pattern of fluctuations matches quantum predictions. Quantum fluctuations in the early universe seeded all structure. All made in stars, all following quantum rules. It has enough hydrogen to last another 5 billion years. But even then, zero-point energy will prevent complete stillness. Black holes are the ultimate endpoint. Once formed, nothing escapes, not even light. The event horizon is the point of no return. Inside, space-time curvature is extreme. The singularity at the center is a point of infinite density, or so general relativity predicts. But quantum mechanics suggests something different. Stephen Hawking showed in 1974 that black holes emit radiation, Hawking radiation. Quantum effects near the event horizon create particle-antiparticle pairs. One falls in, one escapes, the black hole loses mass. Over immense timescales, black holes evaporate, detected by observing stellar orbits. Reinhard Genzel and Andrea Ghez shared the 2020 Nobel Prize for this work. The signal matched general relativity predictions. Kip Thorne, Rainer Weiss, and Barry Barish won the 2017 Nobel Prize. String theory proposes fundamental strings vibrating in 10 dimensions. Loop quantum gravity quantizes space-time itself. Other approaches exist. None are experimentally confirmed. Rules that seemed bizarre and counterintuitive. Rules that predicted and explained phenomena no one anticipated. Scientists at the University of Waterloo and Perimeter Institute successfully teleported energy using vacuum entanglement. Energy was extracted from the ground state by exploiting quantum correlations. Not free energy. Energy conservation held. But the experiment demonstrated vacuum energy is accessible and manipulable under controlled conditions, published in Physical Review letters. Strontium atoms trapped in optical lattices. The clocks are accurate to 1 part in 10 to the 18th. They lose less than 1 second over the age of the universe. These clocks test general relativity. Gravitational time dilation affects clock rates. Elevate a clock by a centimeter and time runs faster. The difference is measurable. Quantum mechanics and general relativity meet in precision measurement. Observations show galaxies rotating faster than visible matter allows. Something invisible provides extra gravity. Candidates include weakly interacting massive particles, axions, primordial black holes. None are confirmed. Detection experiments run in underground labs, shielded from cosmic rays, waiting for a dark matter particle to scatter off a nucleus. So far, nothing. The search continues. The universe's expansion is accelerating. Something pushes galaxies apart. Dark energy makes up 68% of the universe's energy budget. Its nature is unknown. The cosmological constant is one possibility, vacuum energy. But the calculated vacuum energy is 10 to the 123 times too large. This is the worst prediction in physics. Something is missing. Perhaps quantum gravity will explain it. Quantum field theory treats particles as excitations of fields. The electron field pervades all space. An electron is a ripple in that field. The photon field carries electromagnetic waves. The Higgs field gives particles mass. Discovered at CERN in 2012, the Higgs boson is an excitation of the Higgs field. Peter Higgs and Francois Englert predicted it in 1964. They won the Nobel Prize in 2013. The standard model of particle physics catalogs all known particles and forces. 12 fermions, 6 quarks, 6 leptons, 4 force carriers, photon, W boson, Z boson, gluon, the Higgs boson. Gravity is excluded. No quantum theory of gravity exists. The standard model has been tested to incredible precision. But it is incomplete. It does not explain dark matter. It does not explain neutrino masses. It does not unify with gravity. Beyond the standard model, theories abound. Supersymmetry proposes every particle has a superpartner, not detected. Extra dimensions could exist, curled up at tiny scales. String theory requires them, no evidence yet. Grand unified theories attempt to merge forces at high energies. Proton decay is predicted, not observed. Entanglement. These principles are tested daily, in every atom, in every particle accelerator, in every quantum device. They have never failed. They are not approximations. They are the way reality works at small scales. The review detailed modern applications from quantum cryptography to gravitational wave detection. It confirmed no experimental violation has ever been documented. The principle remains fundamental. The strong force binds nuclei despite electromagnetic repulsion. Quantum tunneling allows decay and fusion. Degeneracy pressure supports white dwarfs and neutron stars. Every photon hitting your eye, every force holding matter together. In September 2025, researchers at MIT published in Nature findings on quantum coherence in biological systems. They demonstrated quantum effects persisting in photosynthetic complexes at room temperature, longer than previously thought possible. The study used femtosecond laser pulses in advanced spectroscopy. It showed quantum mechanics operates not just in cold labs, but in living organisms. Evolution exploited quantum rules. The universe runs on quantum mechanics, from the smallest particles to the largest stars, from the earliest moments of the Big Bang to the distant future of black hole evaporation. Quantum rules are not some exotic corner of physics. They are physics. Classical mechanics is the approximation, valid for large, slow objects. But fundamentally, everything is quantum. In the New York subway system, quantum effects power the train's electronic controls. In Sao Paulo's hospitals, MRI machines exploit nuclear spin. In Tokyo's semiconductor fabs, quantum tunneling determines transistor behavior. In Mumbai's optical networks, photons entangle for secure communication. In Berlin's research institutes, quantum computers tackle optimization problems. In Melbourne's astronomy labs, quantum mechanics interprets cosmic data. None of this was known 200 years ago. Classical physics dominated. Newton's laws, Maxwell's equations, thermodynamics, all seemed complete. Then cracks appeared. Blackbody radiation did not match predictions. Atomic spectra showed discrete lines. Photoelectric effect defied classical explanation. Atoms should collapse. Einstein explained the photoelectric effect in 1905. Bohr quantized atomic orbits in 1913. De Broglie proposed matter waves in 1923. Heisenberg developed matrix mechanics in 1925. Schrödinger developed wave mechanics in 1926. Born interpreted the wave function as probability in 1926. Dirac unified quantum mechanics and relativity in 1928. By 1930, the framework existed. Quantum mechanics was complete, predictions flowed, experiments confirmed, applications followed, transistors, lasers, nuclear power, MRI, quantum computing, all based on principles discovered in those decades. They held in 1967 when Dyson and Leonard proved stability. They hold now, they will hold tomorrow. The rules are not temporary, they are built into the fabric of reality. Electrons delocalized, but atoms remain distinct. Nuclei did not merge. Quantum mechanics held even under such extremes. Quantum mechanics governs every interaction. Reproducible, universal. Every rule that keeps you from collapsing is a consequence of wave functions, operators, and eigenvalues. Schrödinger's equation determines how states evolve. The Born rule determines measurement probabilities. The Pauli principle determines electron configurations. The uncertainty principle determines position momentum trade-offs. They are equations that calculate observable phenomena. They predict spectral lines to 16 decimal places. They predict particle masses. They predict decay rates. They predict reaction cross-sections. The simulation confirmed that without the Pauli Exclusion Principle, the atoms would collapse. The computational result matched theoretical predictions from 1967, published in Science Advances. Wave functions must satisfy boundary conditions. Energy levels must be quantized. Degeneracy pressure must balance gravity in white dwarfs. Atoms do not collapse because the universe is quantum. Quantum mechanics stops the collapse. Simple rules. Discovered through decades of effort, tested through countless experiments, applied in technologies you use daily, they are the foundation. Without them, nothing. Handwritten entries from February 1925 show his thinking process. He wrestled with spectral data. He tried different quantum number assignments. On February 16, he wrote the exclusion rule. He tested it against known elements. It worked. He published 2 weeks later. The principle that stabilizes all matter emerged from one physicist analyzing atomic spectra. That principle, combined with Heisenberg's uncertainty and the mathematics of quantum fields, explains why you exist, why matter exists, why the universe is not a collapsed singularity. The rules are simple. The consequences vast. Atoms hold. Reality persists. Quantum mechanics reigns.